So in this section, I'm going to be talking about work and energy. Okay, so work and energy are both, let me use this, are both expressed in joules right here. So energy is like something that an object has. Maybe it's, and I'll talk about these in just a moment here. The different types of energy. Kinetic energy, meaning like how fast something is going. Potential energy, for example, is like how high up something is. So if something is higher, the higher up something goes, it has more and more potential energy. Something can have chemical energy, which is like the energy between the bonds of an atom. Thermal energy, like how hot it is, or nuclear energy, etc. So typically when people talk about energy, they think, oh, there's only two types of energy, kinetic and potential. But no, there's actually multiple types of energy, but you compute them differently. So kinetic energy, of course, is 1/2 mv squared. M is, of course, the mass of the object, and then v is the velocity squared. Potential, of course, is the mass. G is the gravitational constant, 9.8 meters per second squared, and height is how high it up is. So if something is here, it has some potential energy, but if it's higher up, it has even more potential energy. And obviously kinetics, the faster something goes, the more energy it has. And then of course these other types of energy have their own equations for figuring out their specific energy types. So things have energy. But then there's the other thing called work. And what's work? Work is basically I like to think of work as a verb, and energy as like a noun or like an attribute. So energy is like an attribute of something. So something has some amount of energy. That's just what it has, okay? But work is like the driving force, so to speak, that causes energy to change. So if you want energy to be added to something or subtracted or changed from, say, kinetic to potential, from potential to chemical, from chemical to thermal, for example, if you want to change anything about energy, that requires work. So work is the change agent, all right? So energy is something that something has, right? It's like a property. Oh, I have 10 joules of energy, or this object here has 50 joules of energy, or 100 joules of energy, okay? That's just what it has. It's like an attribute. But work is the thing that changes it, okay? So if you want energy to change, like in how much it has, or the type of energy, then you need work. Okay, so work is expressed in joules, just like energy. They're both different sides of the same coin, so they're both in joules, right? So something may have 100 joules of energy, but in order to do work on something, work may require 50 joules of energy. So work, you could think of energy as like money, like a savings account. So in your savings account, you have $100, but then you want to do something with that money, right? It doesn't do you any good for that money just to sit in your savings account. Or checking account. You want to like do something with it, and so the doing something is spending money. So the work is spending the money or spending the energy, and the energy is like your savings account. Okay, so so work will add or subtract energy. Okay, and you can change. So this means you can have something that has 50 joules of kinetic energy, push it even faster, and now it has 100 joules of kinetic energy. But of course, that work that you just did obviously uses energy. The work, you can use work to change the different types of energy. So you can change kinetic to potential, potential to chemical, chemical to thermal, et cetera, et cetera. Okay, so work is the change agent. So here, anytime you want to change energy, so my final energy state minus my initial energy state. So let's say I started out at 0, no energy, but I ended up at 100. So 100 minus 0 is, of course, is 100. And so that's how much work was done, was 100 joules of energy, because that's how much you put into the system, okay? So all work does is just transfer energy around. Work doesn't keep the energy itself. It doesn't go, oh, I'm going to keep this energy. No, it just transforms the energy from one place to another place. So some object had maybe 0 joules of energy, and now it has 100. Due to this work. Okay, so work is the change in energy. All right. Now, if, for example, you want to move a particle, Obviously, if you want to move something, that's going to require some energy. And so, so the formula for that is that obviously it's going to require some work. Is it's force, basically it's force times distance. Okay, S is distance here, or displacement. So if F is like in a straight line, because remember F is a vector, displacement's a vector. If F is going in the same direction as S, like this, let's say F is 3 and S is 5, 3 and 5, you would just multiply them. 3 times 5 is 15. So the amount of work would be 15 joules, okay? But if F is at a different angle than S right here, so if F is at like this angle here, and then S is like straight, remember, because they're vectors. If they're not parallel to each other, right, like parallel like this, if they're not parallel, and then in this case here they're not parallel, then use the dot product. So F is a vector, S is a vector, just do the dot product of them, and you'll figure out your work, okay, which is in joules. So this is it. This is what we're talking about now, is just moving a particle. Something is moving, right? Which obviously has to do with kinetic energy. So this Fs is not necessarily applied to these other things. This just applies to just moving a particle. Okay, so if you have, like I said, if your force is just a vector and your displacement is just a vector, then great, you just do the dot product, boom, you got your work, no problem. But what if what if this force right here is not just a number? What if it's an actual function? What if it looks like this, for example? And then here, your x is your displacement. So let's say you're pushing, your forces, you're pushing something, with newtons. Let's say you're pushing something. This is the displacement. You went 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, 6 meters, 7 meters. You're pushing something. And as you're pushing it, you can see your forces going up, right? The force is a little bit, and then it's higher. And then for flat lines, it gets higher and higher, meaning your force is variable, right? The force is variable over this displacement. So the question is, well, how do you find the work? Well, remember, work is essentially force times distance. So this is force times this. So think of this as if this were straight like this would just be a rectangle, right? You're just finding the area, right? But here, because this is a curvy line, you're not going to multiply just this times this, nice rectangle. No. You're going to have to integrate, right? So whatever f of x is, whatever this function is, just integrate it, right? From this point to this point, and that's your work, okay? So if you have just a single number, f, if you have f as a vector and s as a displacement vector, great, then just do the dot product. But if f happens to be a function of x, then your best bet is just to integrate from starting point, from starting displacement to the ending displacement, and then that'll be your work. Now, when you're doing this with a spring, so a spring, right? A spring can be compressed or expanded, right, or stretched. And so, let's say here you are, and you want to, let's say, stretch a spring. Okay, so over some displacement. So you're starting out stretching, and remember, this is the force right here. So you're stretching it just a little bit, and so does it require? And so does it require a lot of force? Does it require a lot of force to pull initially? No. But as you pull the spring, it's going to get harder and harder and harder to pull, right? And so here, this is still force, which is variable, but it's at a slope, right? The force is sloped. It's a linear slope, right? And so this slope here is K, which is the constant of your spring. So all springs have constants, and if you want to know what the constant is, it's just the slope of this line. Okay, and so if you have the slope of this line K, which is your spring constant, and you know your displacement here, so that's just your slope, and this is your displacement here. You can easily find your work. Okay, so work is still the area under the curve, but I'm just showing here that the actual slope in the case of a spring is the K, is the constant. Okay. Now we're going to work on a problem that uses concepts of work and energy. Okay, so in this problem here, it's called proton bombardment, or what's going to happen is there's a proton with some mass, and it's going to be propelled at initial speed of 3 times 10 to the 5 meters per second. Basically, the speed of light, which is 300,000 meters per second, which is essentially what this is. So there's a proton going the speed of light, and it's directed towards a uranium nucleus 5 meters away, and the proton is repelled by the nucleus with some force right here, and then this is what the number is. And it says assume that the uranium nucleus remains at rest, and then it asks a couple of questions like what's the speed of the proton as it gets like really, so 8 times 10 to the minus 10th is like, almost 0, so really close to the nucleus. What's its speed here? Because it's like here it's going the speed of light, so here but it's 5 meters away, so as it gets really close, what's its speed? And then it says as a proton approaches the nucleus, the repulsive force should slow it down until it comes to rest, which means a velocity of 0. At which point the proton moves away from the nucleus. How close does it get? Okay. So basically, what we have here is we have a problem where. And this is only happening in the x direction. This is only happening horizontally. There's no vertical component here. So you can imagine here's a line. You can imagine this is a proton, P, and it's traveling this direction, and it's going essentially at the speed of light, 3 times 10 to the. Let me just double check. Yeah, 3 times 10 to the 5th meters per second, which is basically the speed of light. So there's this proton here, and I'll just color it like that. So that's the proton, and then over here is an atom. So we'll draw some orbitals like this, and yeah, then we'll color it to look like this. So this is a uranium atom, right here. This is a uranium atom, and the proton is fired at it. Okay, so what's the proton going to do? It's going to go like this. It's going to really fast. And as it's getting closer, it's going to slow down, and then it's going to stop, and then it's going to go back in the opposite direction. So by the time it's back to here, it should be going the speed of light, or 3 times 10 to the 5 meters per second. So it's going to go really fast, slow, stop, and then go back. And so what we're trying to do is we're trying to figure out, what are the mechanics of this? What are the mechanics of this proton? Can we model it? Okay, so that's what we're going to do. Okay, so it told us a couple of things. It told us how fast this thing is going, so we know that, and we know its mass. It told us that 1.67 times 10 to the minus 27 kilograms. So we know how fast it's going. We know its mass, and then we also know about this force. There's some force that's pushing this way, right? So if I were to draw that, so there's a force that's pushing, there's a force pushing in this direction. So the proton is moving in this direction. Now, is the proton accelerating? So as it's moving, it has a velocity, but is it accelerating? No. There's no acceleration, i.e. there's no force behind the proton. The proton is just moving, right? So the proton is just moving, but there's no acceleration. There's no acceleration associated with this. So that means there's no force associated with this proton. So it's just moving. Whatever his speed was before, he's just moving at the same speed. Until, of course, he gets hit by some opposing force, which is this uranium. So the uranium atom is going to create this force that's going to cause the proton to slow down. So the proton has no acceleration, but this force from the uranium atom is actually going to cause an acceleration, a deceleration, right? If the force wasn't here, then the proton would just continue moving along his merry way, assuming, of course, he didn't run into any other forces. So this force is going to cause this proton to deaccelerate until it reaches 0. Okay, so like I said, we know a couple things. We know the velocity, we know the mass, and then we know this force here. So I'm going to basically solve this problem 2 different ways. One, I'm going to solve it using differential equations, and which I think is the more appropriate way to solve this problem. But there's another way to solve it. Well, there's probably multiple ways of solving it. The other way I'm going to solve it is using probably how the person that wrote the textbook assumed you would solve it, which is like figuring out the energies, like, oh, what's the energy of this? What's the energy of this? What's the what's the energy of this thing slowing down? And so basically using like work and energy to solve the problem. Okay. And so instead, I'm going to do it two ways: one, differential equations, and then one using energy, work and energy. Okay, differential equations. How could you solve this problem? Well, basically what we want to know with this proton is we want to know, like, we know its speed here, but what's its speed when it gets to here? And when does it slow down? Like, when is its essentially what's its velocity here, and then what's its velocity here? So essentially we want to know, like, what's the, how can I model the velocity of this proton? Okay, but it's given me force. So can I somehow take this force equation and turn it into a velocity equation? And so normally you could, right? You could take force as a function of time, and you could divide by the mass, right? Because if you, I'll erase this in a minute, but remember, force is equal to mass times acceleration. So I have the force, yes, and I have the mass, yes. So I could, because that's given, so I could divide by the mass, and so therefore you end up with acceleration. Okay, so if you divide by mass, you have acceleration. So now I have acceleration as a function of time, which is cool. And then from acceleration, what can you do? Well, then you can integrate. You can integrate that. And if you do that, then you'll have velocity as a function of time. And then you can integrate that. And then you can find position as a function of time. And then I'll just erase this guy right here. Yeah, erase all that. So that's how you could do it. You could start with force, divide by the mass, get acceleration, integrate, velocity, integrate, position. Perfect, no problem. There is a problem, though. The problem is that this function that I have here, right here, is a function in x. So if you give this f function, this force function, in x, a position in x, right, back and forth, the x, y. So well, here it's x. If you give it an x, it'll tell you the force. So, but this one is, if you give it a time, it'll tell you the force. Okay, so that's cool. But the other one is, it's not that. It's a function not of time. It's a function of x. So that function is f, the force, is a function in x. Right, because we're only moving in the x plane, or the x axis. We're not going up and down y or z. We're just moving in one axis, which is x. So this x, the function of x, is actually 2.12 times 10 to the minus 26 over x squared. And this is in newtons, right? So all forces are in newtons. So this is that's its unit. So that's what this thing looks like. Now, so like I said, this thing is actually, it's a force not of t, but it's of x. So if you give it an x, it'll give you a force in newtons. But if you give it time, well, that doesn't even work. So it doesn't want time. It just wants x. But here it does want time. Okay, so somehow I would like to be able to maybe somehow figure out how to create this velocity, because that's what I want. I'm trying to find velocity. But I have the force as a function of x instead. That seems tricky. Okay, so we'll figure that out. But what I want to do, though, is I'd like to maybe graph this function out. Like, what does it kind of look like? So what it looks like is, if I do this, and so, and then what I should also mention is, what does x mean? What does x mean? X means how far you are away from this atom. So if you're like really close, essentially this is 0. This is the origin. So if you're like here, you're a little bit farther away. So this is like, maybe 1 meter, 2 meters, 3 meters, 4 meters, 5. Remember, this is 5 meters away. But this is 0. So the origin is considered the actual atom itself. The origin is the atom. So if we come back to this thing and I say, what is 0? This is the x-axis in meters. So if I'm 0 meters away, and then we also have 5 meters. If I'm 0 meters away, what's the force acting on this particle? If the particle were like essentially right inside the nucleus, what would that force look like? Well, you can see here that from this function, that if this were 0, essentially if you were right inside the nucleus, it's 0 squared, which is 0, and so it's this number here divided by 0, which is undefined. So that means there is no force. So if you were to ask what is the force right here at 0, essentially in the nucleus, it's undefined. But if you're like a little bit away from 0, like you're a little bit away from the atom, then there is some number here, right? And so what you have to look at from here is if this number is like really, really, really small, then this number is big. So if this number is really small, then this is big. So it's like up here somewhere. But if this number is big, then this number is small. Okay, so it's going to look, kind of like this. It's going to look kind of like that. So meaning the force is going to start out very strong as you're close to the nucleus, which kind of makes sense, right? Because the nucleus, that's where all the force comes from, is the nucleus. So if you're close to it, yeah, the force, and this is, so I should mention this. This is force in newtons. Okay, so if you're really close to the nucleus, yeah, you have a strong force. But as you go farther and farther and farther away here from the nucleus, then that force is going to drop off. Okay, and if you're 5 meters away, remember, I don't know what the force is, but I do know that the speed is the speed of light. Okay, so this is just a little. So here's the graph, the force as a function of x, and this is just kind of what it looks like. Now, what I'd like to do is, could you take this, remember, I'm trying to take this force and find velocity, this force function, and I want to, so I've modeled this force as a function of x, but I'd like to have velocity. As a function of x, right? Because what I'd like to do is instead of this being x here and f here, I'd like to have x here and v here. So as I move further and further away from the nucleus, I can tell you what the velocity is instead of the force. So instead of f of t and v of t, I want, say, f of x and v of x, okay? So what I can do, though, is I can take, remember, F equals ma, just like I did just a moment ago, right? And I can divide by m, and I'll have a. Right, so then I have a equals f over m. So I can just take this function here, 2.12 times 10 to the minus 26 over x squared, and just divide that by m, right? And then that will give you acceleration. So acceleration then, as a function of x, is just 2.12 times 10, that's really a 2, to the minus 26 over x squared. And then you do that all over your mass, which happens to be 1.67. 1.67 times 10 to the minus 27th. And so you remember how to divide. This number actually ends up going, this number here ends up flipping around. And so you just like 1 over 1.67. That's a point. Times 10 to the minus 27. Okay, so you can just kind of get rid of that. So this, you can think of it essentially as you're doing 2.12 times 10 to the minus 26 divided by 1.67. That's effectively what you're doing. And when you do that, you will get a of x, acceleration as a function of x, not of time, equals 12.69. 12.69 over x squared. Okay? So I had f of x, which is this, and then I created a of x, which is that, by dividing by m. Now what I'd like to do is find velocity. But what you're normally used used to is that acceleration is what? Acceleration is the change in velocity over time, the instantaneous change in velocity over time, or the derivative of velocity over dv over dt, right? Okay, so that's cool, but I would like to, instead of doing this, what I'd like to do is I'd like to introduce x into this equation instead. So what if I did this? What if I said dv over something times something over dt? So I have this here, which is here, dv, and I have dt, which is here. And I'd like to put something here and something here that would cancel out. That'll cancel out. That will equal this. It'll still be. I'm still making this. I'm just sort of changing it around. Okay. So what I can do is I could say, hey, what if I instead of dv dt, I could do dv dx. So the instantaneous change in velocity with respect to x, so velocity with respect to x, times the change in x, or position, with respect to time, okay? And so now I've essentially changed dv dt to dv dx times dx dt. This is just using the chain rule, right? Okay, so you can do this. So if you did do that, so I'm just going to write this down here. So acceleration is equal to dv dx times dx dt. Okay, so we know what acceleration is. Acceleration is what I had just a moment ago, which is 12.69, right? This is from here. I'm just sort of bringing it down, okay? 12.69 over x squared equals dv dx times dx dt, okay? Now you'll notice something here, is that dx dt is actually just velocity, right? This is just velocity. So if I can kind of remove that, this is just velocity. Okay, so remember, change in position over change in time is just velocity. So I can just replace that with just v. Okay, so now what I'd like to do is I would like to take this dx, which I have right here, and then multiply both sides by dx, right? Multiply this side by dx, multiply this side by dx, right? And then I'll get rid of this dx here, and I'll get rid of this dx here, and then I'll have 12.69 over x squared dx equals v dv. Okay, and this sort of looks like a calculus problem, right? And so what I'd like to do is I would like to just get rid of this. I want to get rid of this dv part, and I just want to have just velocity, right? All I want to do is create a function. I want to create a velocity function. Is this a velocity function over here? No, it's v dv. So how could I just get rid of the dv part? Well, I can just integrate it, right? So if I integrate this, if I integrate one side, then I have to integrate the other side, okay? So if I do that, then if you integrate v dv, that just ends up with, remember, that's kind of like v to the 1. So you have v squared over 2. Okay. And then if you want to do this one on the left, then what you can do is you can pull the 12.69. It's a constant times the integral of, and we could just do x to the minus 2. Just put it on the top, if you will, and its exponent is -2, and then this is dx, of course. Right? Okay. So then what you have to do is you have to integrate that. So what you're going to do is you're going to take this -2 and make that a -1. Right? So this ends up being x to the -1. Now, because this is -1 here, that means on the bottom you also have to do -1. Remember, because whatever you put on top, you have to put on the bottom. And so this, of course, just equals -1 over x. Okay, this just equals negative 1 over x. And then, of course, you have to multiply this back in. So then you have, let's just do it over here. Then you have 12.69 negative over x, okay? And so then you have that, and then on the other side, you have equals v squared over 2. Now there is something to be aware of, is that when you integrate something, because this is not a definite integral, it's an indefinite integral, you have to add the constant of integration, okay? And so meaning I have velocity over here. I'm trying to find velocity. So like what's the initial velocity, right? What are the initial conditions? Now, it actually did give us some initial conditions. It told us that here an initial speed of 3 times 10 to the 5, or the speed of light, and it's 5 meters away. So I know a distance and I know velocity. So that's like some initial conditions. And so we have that. So we can apply that to this. So what we're going to do though is we're going to add plus c here, which is some constant of integration, okay? You can add it actually to either side, but I'm going to add it to this side over here. Now, what we're going to do though is so remember the c is a constant of integration because we just integrated, of course. Now I'm going to take this 2 and multiply both sides by 2, right? So this goes away, and then multiply this side by 2, and you end up with negative 20. So 12 times 2, which is 25.4, essentially 25.4 over x plus, and then you have 2c, or you could just, if you wanted to, just say c. It's just some constant. Like you don't know what it is. You don't know what it is, so I'm just going to leave it c. Okay, it's just some value. Okay, equals v squared. Okay, and then now, of course, we have to take the square root of all that stuff. And now we have v equals, the velocity equals square root of negative 25.4 over x plus some c. And the c is some constant, and I don't know what that constant is, okay? So that's the velocity. Now, now you might be wondering, well, I just took the square root of something. Do I need positive or negative? No, we're just dealing with positive velocities, okay? Because remember, velocity is a vector. It is a vector. I'm just trying to find my picture again, right? So we know that this thing is coming in like this. And so the velocity is going to be whatever. It's going to be 300,000. It's going to go to 0, and then it's going to go back. Does that make sense? It's going to be some high value, speed of light. It's going to come to 0, and then it's going to go backwards. So it's never going to be negative. So the velocity isn't going to be negative. It's just going to be, well, I should say this. This thing is actually pointing in this direction here. And in this way, it's pointing in the opposite direction. So in that case, yeah. So in that case, the velocity would be, so you're like the velocity of what? Is the velocity of this thing the velocity of the force? No, the velocity is the velocity of the proton. Okay, so yeah, you could say that the velocity of this thing, because it's pointing in this direction, is, let's say, positive, and then once you flip it around, it would be negative, okay? So that's just something to be aware of. We can discuss that in a later video, okay? So I have this velocity here, right? And it's negative 25.4 over x plus c. Now I don't know what c is. Now here's the trick. This is what I would do when trying to figure out this constant. When trying to figure out this constant, is solve this equation, meaning what you should do is put in a value for v and put in a value for x, supply those values for v and for x, and then just solve for c. And we can do that, right? Because remember up here, 5 meters away, 3 times 10 to the 5th. So what we could do is for this value that we're looking for, is we could say, all right, v is 3 times 10 to the 5th. And then for x, we could say you're 5 meters away. 5 meters away, okay? And so if you put those in there and you just solve for c, of course this is just algebra, right? And then you solve for c ends up being 9. Yeah, it's I'm just looking at my quotes. Yeah, it's 9 times 10 to the 10th. It's 9 times 10 to the 10th. So if you supply this velocity, which they gave you, and this value here, these are some initial conditions, or some conditions they gave us, then you can just solve for c, and c equals this. Okay? So then you can rewrite your equation as the final one, as velocity as a function of x is the square root of negative 25. Hold on. 25 point. Hold on, that's bad. Sorry. 25.4 over x plus 9 times 10 to the 10th. And that's it. And so now that you have that, you could essentially solve all the problems that you're looking for. You're like, oh, what is the velocity? Because the question was, what's the velocity when it's 5 meters away? What's the velocity when it's this meters away? All you have to do, right, is just pop in this value, your distance, and you'll get a value, right? You'll get a velocity, okay? And conversely, if you're looking, you're like, oh, well, where does it stop at? Remember, because the proton is going, and then it's going to stop, and then it's going to start going back, right? Okay, well, where's it going to stop at? Well, in that case here, this would be 0, right? Because your velocity is 0. And you just solve for x. You solve for x, okay? So basically, in the question 1 and question 3 are pass in an x and get a velocity out, right? Pass this in and you'll get a velocity out. The question B basically means is don't do that. Question B is make this thing 0 and then just solve for x, okay? And then I'm not going to give you the answer. This is just basic algebra, okay? But that's it. So, and let me highlight this thing. So this is your velocity in x. So, just to recap a little bit, I took my force as a function of x, divided by the mass. I got acceleration as a function of x. I took acceleration, which is a change in velocity over time, and I changed that to the change in velocity over x times the change in x over time. Right, this is using the chain rule. And then I said, okay, the acceleration, I know what that is. And dv dx, okay, that's here. And this is just velocity, right? This is just velocity. I multiplied both sides by dx, right? Right here. And then I got dx here. And then I just integrated both sides. I got this, got that. And yeah, and then I had my you have to add your constant of integration here. And then I solved what is my constant of integration by putting some initial conditions in, getting my constant, and then popping that back into the velocity function, and then I got that. Essentially, this is the whole game. Once you have this is essentially modeling the velocity of your proton as it's approaching the nucleus of your uranium atom. This is what you're looking for. Once you have this, all your other problems can be solved from that. Okay, and so now what I'm going to do is I'm going to solve this problem using the concept of work and energy, okay? All right, so the question is, for example, that they gave above was what is the speed when it's, let's say, 8 times 10 to the minus 10. Yeah, 8 times 10 to the minus 10. 8 times 10 to the minus 10. So what's the velocity? So what's the velocity when the position is this? When the position is this? Oh, when it's that far away from the nucleus of the uranium atom. Okay. So remember what I just did a moment ago is I found this velocity function. But let's say you didn't want to do that. You just want to use the concept of work and energy. Okay. So you may remember I have this function this force, which is in newtons, right? And then I have x, or displacement, along the x-axis. And you may remember it looks a little bit like this. Okay? So what I want to do is I want to figure out how much work. So remember, work is the area under the curve. And so what happened is we're going to go from, so the proton is currently 5 meters away. Okay. And it's going to go until it reaches, and this obviously isn't to scale, but to 8 times 10 to the minus 10 meters, right? And so what we're going to do is we're going to find the area under this curve, which is work. Okay? So remember, work, the area under the force versus x graph, the area under that curve is work. Okay? So what is that? So all you have to do is, well, so the force function, remember, from before, is 2.12 times 10 to the minus 26, right? Let's double check that. Yeah, over x squared. Over x squared. So that's the function. So that's what this blue line represents, all right? So all I have to do is integrate. Essentially, all I have to do is integrate from where? I need the lower position. And well, that's 8 times 10 to the minus 10 to 5. And this, of course, is in meters, right? Because we're going along the x-axis. And I have to integrate the function f, which is 2.12 times 10 to the minus 26 x squared. And this is in x with respect to x, so this is dx. Okay? And so, yeah, so basically this is just a definite integral, because we have our bounds, which is here and here. Okay? And so so I'm doing the area under the curve, which is work, right? So that's equal to work. And so if you just do this integral, you'll end up with 2.65. 2.65 times 10 to the minus 17. Okay, now this is work, so it's in joules. So that's how much work the uranium nucleus did on this proton. Okay, now the proton came in and it had a certain velocity, right? Remember this proton? Here it is, and it's coming in and it has a certain velocity, 3 times 10 to the 5. But how much energy does that have, right? Does it have energy? Yes, it has moving, so it has kinetic energy. And so you may remember that kinetic energy equals 1/2 mv squared. So I know it. So the mass was given. Remember, the mass was given. It was 1.67 times 10 to the minus 27. So we have the mass. Okay, we have the mass, and all we're looking for is just velocity. Okay, so this is a very simple. We have mass, so we're looking for this. We don't want half as a 0.5. Of course, we have mass, and then the velocity is this. So we have everything we need. Okay, so if you do that, you'll end up with the kinetic energy is equal to 7.515. 7.515 times 10 to the minus 17. Okay, joules. So this is energy. Over here, this is energy that it has, and then over here is work. This is energy, and then this is how much work was done. Remember, work transforms energy, right? It transforms energy. So how I like to think about this as a bar graph. It might be, useful. So this is the kinetic energy of the proton, which is 7.515 times 10 to the minus 17. Okay, and this is in joules. Now this is how much energy it had. And so what we're going to do is we're going to slow it down. So this work, as you can probably imagine, is going to slow it down. But how much work did we just do? Well, we did this much work. So let's say this is 2.65, that's what we had here, times 10 to the minus 17, and this is in joules as well too. So that's this. So this is kinetic energy. This here is work, right? This here is work. And so this work that I did on the kinetic energy is going to make the kinetic energy less. So now essentially what we have is we have leftover energy. So there's some remaining energy, right? Which is just this part. So if you take this right here minus this, you'll end up with this, okay? Which is just 4.65. No, so 4.86. 4.86 times 10 to the minus 17, okay? So now, I had, this is the initial energy. I sucked away some kinetic energy using work, like I pulled it away, pulled this much kinetic energy using work, okay? I was repelling it, so I used this much work. I consumed essentially this much kinetic energy. So now all I only have is this much kinetic energy. But if you know this much kinetic, if you have this, if you know your kinetic energy, KE, is equal to 1/2 mv squared, and you know your kinetic energy is 4.86 times 10 to the minus 17 joules, then you can say 1/2 times your mass, which is, I should write this down, 1.67 1.67 times 10 to the minus 27 kilograms. All right, this is this, times velocity squared. So if you do that, you can see I have everything that I need except for velocity, which is what I'm looking for. And so if you do that, you'll end up with in this case, the velocity is 241,378 meters per second. So just to recap, I found the initial energy of the proton based on how fast it's going, right? Based on its velocity and its mass. Then I did work on it. Well, I didn't, but the nucleus of the uranium atom did work on the proton. How much work did it do? This much work. And so I'm going to subtract this much energy or this much work or this much energy from this energy. This is the total energy. I'm subtracting this from it. And now this is the leftover energy. Once I have the leftover energy, I can just pop it into this equation here and find out its velocity. Okay. The last thing that I want to do is, well, part B basically said, oh, okay, so you have this proton here, and it's going towards this, right? It's going towards this atom. But where does it stop? Because it's going to go, and it's going to turn around, right? It's going to turn around. Where does it turn around at, right? How far, if you want to what's this distance here? Change in x. What's this distance here? Looks like a box. From the center of the atom to when it turns around. So this is 0, right? So this velocity is 0. So what you could do is you could say oh, here I have, let's say I have 100 joules. I don't, but let's say I have 100 joules of kinetic energy. Well, when I get to here, I have 0 joules of kinetic energy. So whatever I have here, I'm just going to take all of it away till I have 0. Why? Because remember, your energy, if it was 0, equals 1/2 mv squared. Well, if you do this, then your velocity is going to end up being 0 too. So if your energy is 0 joules, your velocity is also 0. Okay. So if my kinetic energy is 7.515 times 10 to the minus 17 joules, right? Then what I want to know is what is the area under the curve from, where am I starting from? Where am I starting from? A. That means I don't know where I'm starting from. And I'm going to use my force function, which is 2.12 times 10 to the minus 26 over x squared dx. So basically what I want to know is how much work do I need to do? This here says, remember, because this is my force function with respect to x, my displacement. Okay, how much work do I need to do in order to get? Remember, and this is how much kinetic energy I have right now. Initially, this is how much energy I have. And what I want to do is I want to drain all of this to zero. I want to drain this to zero. So how much work do I need to do to where this drains to zero? So I need to make this equal this, okay? Because I want to drain it. So essentially what we're going to do here is we're going to integrate this function. Remember this function here? It started off at 5, and it's going to go to where it meets. Let me just change this color to this or something like this. Something like this. This is A. This is A. And so when this thing integrates here, this area under the curve, this hopefully will be 7.515 times 10 to the minus 17 joules. Okay. But the problem is I don't know what A is. I don't know what A is. And so, but I can just pop it into there. I can just say, okay, well, I know this. This is my initial kinetic energy. I'm trying to drain that away. I know that I'm going to 5. I do know that. And I do know my function, which looks like this. The only thing I don't know is A. And so now you just have an equation, right, where you're solving for A. Okay? And that's pretty easy. And then once you do that, once you just solve it, that's which, like I said, is just basic algebra. Well, some calculus, obviously, and some algebra. You end up with A. The value of A is equal to 2.82 times 10 to the minus 10 meters. Okay? That's this. So the proton is gonna go from 5 meters away to 2.82 times 10 to the minus 10th meter. So like really, really, really close to the nucleus of the atom. And at that point, it will stop and then turn around. Okay, stop and then turn around. And then start accelerating again. Because what'll happen, of course, is that in this way, here it's getting slower and slower and slower and slower because the radiant is pushing. It's like pushing this way, so it's slowing. But once it turns around, this force is going to cause it to accelerate. So here it's deaccelerating, but here it's going to accelerate. Right? It's going to accelerate away. Okay, and then back when it gets to P again, it'll be back to essentially the speed of light, or 3 times 10 to the 5th. All right, that's it.